But you may remember, one of the things we developed was a conical pendulum question algorithm, a set of steps, right, that you can take and you can apply them pretty much to any conical pendulum question, and it should do you pretty well, okay? Now I should mention, right, algorithms get a bad name. And the reason why they get a bad name is because you can use an algorithm without understanding why it works, right? So if I gave you something like this, b squared minus 4, maybe I'll make that a minus. Okay, so here's a pretty typical quadratic, and you can teach, I think in year 7 is when you first learn algebra and substitution. So you can teach a 12-year-old how to do this. You can say, look, the A and the B and the C, they're meant to be here, here, and here, and then you just have to punch it in, and out you get a number or a pair of numbers at the end, okay? That's an algorithm. And you can crunch through the algorithm and get to the end of the algorithm and get an answer from the algorithm without any understanding at all of why, okay? So what you guys have to make sure is, as we go through these, do you know why we're doing them? Or we'll revisit it after we go through an example of this, okay? So can you remember what were the steps of the algorithm? The first one's the easiest one. Good. You got a diagram. Tell me, remind me what goes on the diagram. Mainly it's forces that we're interested in, okay? Specifically, the physical ones. Give me some examples of physical forces that you'll see. Gravity. Tension in a string. The reaction force off of a surface, okay? So they're all on there. After you've drawn that, then what do? You appeal to some stuff you learned a couple of years ago, trig, or whatever geometry, parallel lines and all that kind of thing. Why are we doing that? What's the point of that? What's the goal?
Horizontal and vertical.
Not yet. We haven't got there yet. We've only just done this. We've just done this. You need to know, forces. Forces are vector quantities, right? They're vector quantities, which means they have two parts to them. What are the two parts? There's a direction, right? And then there's a magnitude, okay? So what you're doing is you work out the direction and magnitude of all of the different forces and you use trig to do it, right? You'll be like, oh, this one's n cos theta, or that one's t sine alpha, or whatever it is, okay? All right, after you've worked all that, then you resolve the forces. And of course you resolve them into... Okay. You resolve them into two different parts, right? What will you expect the vertical forces to resolve to? Remember, it's uniform circular motion. Should be 0. It's not going up and down, okay? It's just making that nice horizontal circle, okay? What does the horizontal force, or the horizontal forces, what do they resolve to? mr omega squared. Or, alternatively, if you don't know what angular velocity is, what's the other way we can write it? mv squared on r. In case what you're given in the question is, oh, it's going around at 2 meters a second or something like that. Okay? So that's what you're expecting. Final step. Solve. Good. Depending on whatever it is that they ask you for, maybe it's the tension or the reaction force or whatever it is, you want to solve the force equations. Okay, now can we just pause for a second? Like I said, algorithms get bad press because sometimes people use them without knowing why you do any of them, right? So why these things, why that order, why are they useful to us? A classic example question is, what's the tension, right? In fact, I'm going to ask you one of these in a second, okay? So what do you need to know in order to solve for this, to work out the tension? Well, clearly you need to know what the force equations are, right? Horizontal and vertical, okay? They'll show you some relationship between tension, gravity, reaction force, whatever, okay? But to get these, well, you had to resolve all of the forces in the first place so that you equate them to these, which is what uniform circular motion does, right? Just like, just like in simple harmonic motion, you'd say, well, it's got to do this. Oops. Right? So you're like, okay, I'll fit it into that, and then I can solve stuff from there, okay? But of course, to work out what any of these quantities are, you need to work out how big they are, and which way they're facing, and what angles are going on. And that's where the trig comes in, right? well, you're not going to be able to do much useful trig or geometry unless you've got a decent diagram that shows you where everything is pointing. Does that make sense? Do you see how there's logic to it? Please, please, don't just do these because I said so. I mean, do them because I said so. But don't do them only because I said so, right? You've got to know why. So, let's apply it. Example, a hemispherical bowl. Let's do it like this. Let's consider this in general terms first, and then I'll put some specific values on it, and we'll solve for a particular kind of thing. Okay. So here you go, typical example. It's a bowl and it's in the shape of half a sphere, so that's nice and easy to work out. Okay. You've got an angle up here, theta. Okay. And you've got this string holding this so that it goes in uniform circular motion. Okay. So let's start. We've got the diagram. I haven't put any forces on here. What forces would you like to suggest for me to draw on? Gravity. Gravity. I'll put tension on in a second. Gravity is usually the first place I start, okay? Because it's always the same every single time. So it's mg down in that direction, okay? The next one suggested was tension, okay? Where's tension going? It's going up along the string, okay? So something like this. And we'll call that T, okay? Tension, gravity, are we done? There's a normal force involved because I'm resting on a surface. But there's a bit of a problem here. Let's go back to our example before. This was from yesterday afternoon of the cone, right? So it's facing up, and I have the, drawing out a circle like so, and then I got out my diary and my keys, and we talked about the reaction force that surface, that any surface, is exerting. And it's a normal force, right? So there's a right angle there. No problems, okay? Except, where does my right angle go at the moment? Which way does it face? Because the problem is, like, depending on, like, if I was here, or here, or here, I'll be facing all different directions, right? So which way am I going? Now, be careful, right? If, for instance, let's just do an example here. Suppose it was spinning super fast, right? So it was up, and the actual particle was over here, right? Okay. So you can see obviously the tension's going up on the string, okay? But here it's a little more clear, right? Because it's a hemisphere. So this part here should be vertical. I didn't draw it very vertical, but you get the idea. So if this is vertical, which way is the normal facing? It should be horizontal, right? Like vertical, perpendicular means horizontal, okay? So you're definitely not going in the same direction as the string, right? So tension is going that way from the string, but the normal force is facing another direction, okay? Now, it's actually not that hard to work out when you think about it. Here's a circle, so now I'm looking right on. So I'm looking kind of at an angle right now, downwards into the bowl, okay? But let's sort of go down a little lower, right? So all I can see is just, well, I'm just going to chop it in half, okay? Now the normal force is going to be perpendicular to the tangent force, right? Because that's what tangents and normals do. But the tangent is perpendicular at the point of contact to what? To the radius, right? So in other words, this normal force, right, wherever I am, it's going to be pointed to the center. That's why if I'm right up here, I'm pointing horizontally to that midpoint right there, okay? I'm actually down here, so in order to draw this force in, I need a bit more information. I sort of cheated you, okay? So I'm going to rub off this green pretend bit. what I really need is, I need the center. I need the center of the, if this ball was a sphere, wouldn't be a very useful ball, but it would have a center about here, wouldn't it? Okay, so I'm going to draw that in. Something like that. So there's the center of that top sort of surface, right? And that, along here, that is the direction that the normal force is going in, right? Perpendicular to the surface of the ball. Okay. So, am I done with my diagram? Have I accounted for all the physical forces? I think it looks good. I think it looks good. You've got the string accounted for, you've got the ball accounted for, you've got gravity accounted for. We're not worrying about friction or anything like that. It's done, okay? So, now I need to appeal to trig and geometry to try and sort these things out. How big are these things, and which direction exactly are they facing, right? So to do that, actually maybe I should put this over here. Okay, I've got my theta up here. I'll need to call this some other angle, because clearly it is some other angle. It's not going to be the same as theta because they're not parallel, right? So I'm just going to call that alpha. Is that all right? Alpha. Now in the past what we've done is we have drawn more horizontal and vertical forces coming off of the particle, because that's where they're acting. Right? So I've got, in this case, I'm going to have a vertical component of tension, and then a vertical component of the normal, and then I'll have a horizontal component of each, just like this, the same. But they're right on top of each other. This is going to be a bad idea. So I'm just going to draw off to the side two separate diagrams. One for the tension and one for the normal. Okay? I'm just trying to make sure my diagrams are clear and not make it all muddled up. Right? Let's do the tension first. Okay? So there's the actual direction of the force, and now I want the horizontal and vertical bits, right? Right angled there. Now look at this diagram here. Where would this triangle be situated? It'd be right in here, right? So that's a vertical there. You've got corresponding angles. So theta is up there. Happy with that? There's T, that's that magnitude, okay, of that tension, right? So you use trig, and you get this, right? What's the upward force? What's the vertical part? It's going to be T cos theta, right? Because this is adjacent to the angle I'm after. So T cos theta in that direction. And then horizontally, T sine theta, because it's opposite. So far, so good. Now let's worry about the normal force, okay? Like so. But you're replaying exactly the same thing, aren't you? Instead of theta, you've got the alpha over there. So alpha in the corner. You can see it starts to get quite automatic, right? Once you know which way things are facing. Okay, so upward here, because this is n, you're going to have n cos alpha. Whoops, I drew that the wrong direction. Sorry, it's going that way. N sine alpha. Sorry, that was a big thing actually. You should note that they are both facing inward, right, toward the ball. Neither of the forces are making it punch through the surface of the ball. That's kind of important. Okay, good. I'm going to resolve them by saying, well, okay, like that, this is step 2 done. The vertical thing should be equal to 0. Let's do that. Okay. So vertically, right, I've got these two going up, and this one going down, and they should cancel out because of Newton's third law. Okay, so that gives me this. T cos theta, then cos alpha. So that's what is happening up and down. And then horizontally, okay, now both of these are going in toward the center. Both going in toward the center. Okay, so when I add them together, let's see, T sine theta and N sine alpha, right? They're both facing that direction. So it'll be this if we know what angular velocity is, or it'll be this if we know what linear velocity is. And right now we don't know anything, so I'll just write both. You happy with that? Okay, so now I'm going to put some numbers on all of this, and I'm going to pose 2 questions to you. So let me write this up, and then I'll give you some time to give it a go yourself, okay? Let me give you some angles and lengths and sine. So then here are my 2 questions. If the particle's circling the ball every 4 seconds, 1, 2, 3, 4. Back to the start. 1, 2, 3, 4. What's the tension in the string? Typical question. This one, a little more interesting. If the particle speeds up, what happens to the tension in the string? And can you account for the reason why it changes the way that it does? Have a think about that. Give that 10 minutes.